Welcome back to the series on sequential decision analytics. This module is on estimation methods. So this module is not actually on a sequential decision problem, but these are tools that are widely used when studying sequential decision problems. So I'm going to start by talking about the different types of functions that we have to estimate. Then a quick overview of approximation strategies. I want to talk about exploiting structure and close with a brief section on batch versus recursive learning. So the functions we may need to estimate, one is approximating the performance of a policy over time. We're making sequences of decisions. Maybe that policy is a function of a set of parameters theta, which means my performance of the objective function is also a function of parameters theta. I may need to approximate that function to help me optimize theta. Second class designing the policy. The policy x is itself a function, and I may need to approximate that using any one of the approximation methods, anywhere from linear models to neural networks. Third, value function approximation. So in the study of sequential decision problems, a very popular method depends on Bellman's equation. We're going to cover that much later, which requires that we approximate the value of being in a state. And we may use a linear or nonlinear or neural networks for this. Designing a cost function approximation. Now, a cost function approximation, one thing that we might do is approximate the cost in the objective function. So I may have a cost where I don't actually have the function. It's not a well-known function. I have to approximate it as a function of theta. Maybe I'm trying to estimate how somebody responds to an incentive. I don't really know the reward structure, but I'm going to approximate that. Another way under cost function approximations is to say, hey, I'm going to solve this linear program. Now, the linear program will solve a deterministic problem, but I like to use it to solve a stochastic problem, and I'm going to do that by parameterizing it in a creative way. And then I have to design that parameterization and then tune it just as we do with any machine learning model. Finally, the transition function describes how we evolve over time. So imagine I'm trying to describe how disease propagates in a population. I actually don't know how it propagates, but what I'm going to do is do what's often done in machine learning. I'm going to make up some function that I think is reasonable. It'll have some tunable parameters, and then I'm going to use observations to try to tune those parameters. Okay, quick overview of approximation strategies. There's three broad classes of approximation strategies: lookup tables, parametric models, which can be linear and nonlinear, and non-parametric models. Let me step through each of these. So lookup tables, let's say I have 5 choices and I have an estimate of the performance of each choice. These might be 5 different catalysts or 5 different people or 5 different drugs when I'm treating a patient. And when I observe one, I learn nothing about the others. Now, correlated beliefs is just the reverse. I try something and I do learn something about others. Maybe there's different drugs that I'm treating a patient with, but they fall in different families. Or maybe I'm purchasing a product like a red short sleeve shirt, but if they're out of it, I might buy a blue short sleeved shirt. So learning about one of the choices will teach me about others. This is actually very common, and it's an exceptionally powerful strategy. Finally, let's say the choices are actually described by a vector of beliefs. Now, so like a human, I could say, hey, I want a particular person to do this job, maybe somebody to build a device or drive a truck. And humans are always described by a vector of attributes. And when you multiply all the different possible vectors of attributes, you get some huge numbers. So what I like to do is work at different levels of aggregation. And what I can do is do estimates at different levels of aggregation and then do a weighted sum of these. This is an exceptionally powerful strategy. I've been very successful using that. Parametric models. So parametric models are where you have a well-defined finite function with a set of unknown parameters. Linear models, which means linear in the parameters, the features phi, x might be a price. Maybe I have demand as a function of price. And the phi functions could be just a constant. It could be just the price or the price squared or the log of price. And if I sum them up and multiply them times a coefficient theta, that's a linear model. If you have smaller ones with hundreds or thousands of parameters, that's what we were working with, especially up through the 80s and 1980s and 1990s. By the 1990s, we were starting to get very large linear models where we realize that many of the parameters are actually zero. We call those sparse additive models. Nonlinear models. A popular nonlinear model is a logistic regression. That's our S-curve that's plotted there. Or maybe a step function. That's actually a nonlinear model. It's not a smooth nonlinear model, but it is a not linear model, and is parameterized by the parameters that determine where the steps happen. You can have shallow neural networks. I'm going to make the distinction between shallow and deep neural networks. Shallow neural networks classify as a parametric model, just like all these others. They're a very general form. I say a shallow neural network because the deep neural networks have a property I'm going to describe in just a minute. Shallow neural networks can approximate very general functions, but not perfectly. Non-parametric models. Non-parametric is basically local approximations, the most popular being locally constant, but I might do locally linear. The first one, kernel regression, I have 2 points at mu1 and mu2, and I have a line approximating the behavior of the function in the vicinity of that point. As you need estimates in between those 2 points or outside of that range, you're going to do a weighted combination of these 2 lines, weighted by this downward sloping kernel. Locally linear models fall in categories like Dirichlet process mixtures or radial basis functions. These are all in the same family of approximations. You have splines. Support vector machines is a class of approximation strategies useful for classification of data, dividing people into different groups. And then you get the deep neural networks. Now, the deep neural networks emerged circa year 2010 for image processing. Deep neural networks fall under the category of non-parametric. The working definition, has been explained to be by my statistician friends, is that in a deep neural network or a non-parametric model is any model where if you have an infinite data set, you can get a perfect approximation of the function. So deep neural networks do have that property that if they are large enough, an infinite data set allows you to get a perfect approximation. Now, by deep neural networks, this actually comes before the large language models, which were dramatically bigger than the deep neural networks that we did around 2010. Now, I want to urge some caution. There's a tendency today to use neural networks for almost anything because you can put in any data and it'll come out with an estimate. Neural networks struggle with noisy observations and structure. So if you have a monotonically increasing function or a convex function and you feed it noisy data, you don't retain those properties. So for example, here's a news vendor problem where I'm going to put a quantity of newspapers X. I'm going to then observe a demand D. I'm going to take the smaller of the two. That's how much I'm going to sell. And D there is a random variable. I have to pick X before I see the D. Now, if you take the expectation of the revenue I'm getting, which is how many newspapers I sell times the price minus the cost, CX, you're going to get that red function. Now, this blue line D is the place where D hat is greater than or equal to X, where the line is where D equals X. Anytime D hat is greater than X, it gets capped. If I order a quantity X and I observe some profits, let's say the demand was less than X, if you take the expectation over all the blue dots, you get that wiggly curve. Now, the true function, if you could get the exact expectation, that's the red function. Now, that red function has some very nice properties. Namely, it's concave. And when we're optimizing, concavity is a great property. If I was trying to optimize the fitted neural network, I would have all kinds of practical problems. There's local optima in there. And so unless you have a virtually infinite data set, you're not going to get that nice red function from a neural network. Here's another function. Demand is a function of price. Well, we made up a function from a logistic regression. That's the black downward sloping curve. So let's pretend that's the exact function. Now let's randomly generate a bunch of prices. And then for each price, I'm going to do a coin flip from the logistic regression and use that probability to say, did I purchase the product, which the probability increases as the price gets smaller, or maybe I didn't. So the red dots are always 0 or 1. So let's take all those red dots fit that and the corresponding price into a neural network, and you get the green line. Now, if you had a large enough data set, you would get the black line. But generally, such as if I'm fitting demands, I don't have an infinite data set, and you're really at risk to get that wacky green line. So exploiting structure. Structure arises all through sequential decision problems. Here's an equipment repair problem where the longer the deterioration, at some point you're going to want to stop and repair. Or if I'm dispatching customers in a queue, if you have a queue length, the longer the queue, if it's short enough, I'm not going to dispatch the vehicle, but once it gets over some limit, I'm going to dispatch. I want to figure out where that step function is, but I know that it's going to be a step function. This is called a monotone function because as the deterioration or the queue length increases, the decision either do nothing or repair rises monotonically, in this case, a step. Here's an extra one, buying electricity, where there's 3 steps. When the price is low enough, I'm going to sell. At a middle range, I do nothing. At a high enough price, low enough price, I'm going to buy, and a high enough price, I'm going to sell, and in between, I do nothing. Another type of monotone function. Monotonicity happens all through sequential decision problems. Health, dosage of diabetes drugs increases with blood sugar. Finance, holding the cash in mutual fund increases with the number of redemptions. Here's a nice monotone function, a little weird. It's got this 45-degree angle where on one side it's just 0, but the other side, it has this series of plateaus that are increasing. This is a bidding problem. You have a low bid and a high bid, and what we want to do is replicate this function. Now, if I just do random samples, and I don't do an infinite number of them, I'm going to get this really odd surface where I have only the places where I've sampled, and then in between, I don't have anything. Now let's use monotonicity as a structure. Let's say I have my surface and I observe the blue dot and I get a value of 10. And I know that everything to the right and above it has to be at least as big as that, so I can fill all of those points in. From one observation, I can fill in this whole plateau and say, well, these all have to be at least 10, so I'll just set them equal to 10. Now, let's say I come in and I get a red dot and I get a 5. Well, the 5 means everything to the left and down has to be 5, so now I'm going to update that. So monotonicity allows you to take a very small number of observations and to update wide ranges of the function with very few function calls. And I don't have to make any assumptions about the function other than exploiting monotonicity. So here's an algorithm learning a function, and you can see how very, very quickly it starts to replicate that monotone function. And this is a fantastically powerful property to have. Here's a function where I have the value of resources, a function number of resources. If I observe one point and I get the slopes, I get the left and right slope, I know that it's a concave function, that the left slope is always going to be steeper than the right slope. Now, if I do this over and over again, over time, I'm going to be able to build up a piecewise linear concave function. This is an exceptionally powerful strategy for wide ranges of resource allocation problems. For example, here's a problem where I have a factory down in Mexico shipping to distribution centers. The problem is I don't know the demand at the distribution center. So what I can do is use these piecewise functions to say, what is the value of inventory at each of the distribution centers? And with really surprisingly few iterations, maybe a dozen or two, I can get pretty good approximations of these piecewise linear functions. Finally, batch versus recursive learning. So if I'm doing lookup tables, let's start on the left-hand side. Batch information says, let's say I have a bunch of observations W, and if I get a small n of these and I sum them up and divide by n, I get an average. This is what we've seen in our introductory statistics books. And if I want the variance, I take the sum of the deviations between W and mu bars, sum them, divide by n minus 1 is the standard formula. Now, we can also do this recursively. So instead of getting a whole big batch, because sometimes I have very large data sets, I might have 100,000 observations, and they're arriving over time, I can exactly recover the batch formulas recursively using these two formulas down below, one for the mean and one for the variance. And they're very simple to implement. I never have to store the entire data set, and it's particularly useful when the data is arriving over time. Now, let's say I have a linear model. There's these standard equations called the normal equations. Capital X here is a matrix. This is standard statistics notation. Every row of the matrix X is a different observation. Every column is a different feature. And this is a standard formula. And by the way, you have to do a matrix inversion, which can be problematic if you have a large number of features. So that X transpose X inverse, if you have a model with 100 features, 100 parameters, you're going to have a 100 by 100 matrix to invert. We're routinely working with models that have thousands or tens of thousands. You can exactly recover that solution from the normal equations using the equations under recursive. This will give you the exact theta n without ever having to do a matrix inversion. There's no matrix inversion is done this sort of magically, which is a really neat result. Bayesian estimation. If you have independent beliefs, here, if you have an observation W, beta here is the precision of the observation, which is 1 over the variance. So I have beta superscript capital W, that's the precision of observations, if I have noisy observations. And then beta n sub x is the precision of the estimate mu bar. So mu bar is my average. The average is a random variable. It has a variance. Take 1 of the variance, it's the precision. When you work in terms of precisions, the updating formulas are just really nice and elegant. Notice how the precision of the estimate always gets bigger, and it gets bigger by the amount beta W. Now, if you have correlated beliefs, now the mu bar becomes a vector. Let's say I have a vector mu bar at iteration n, and then I observe choice x. So the mu bar n plus 1, that's a vector, but it's been updated with an observation of x. So the w n plus 1 of x, that's a number. That's the scalar number where I observed a particular drug or a particular person or a particular sales price. The mu bar is a vector. So the vector mu bar updated with the observation from x is equal to the old mu bar, which is a vector. The capital sigma is a matrix. That's the covariance matrix. And you have updating formulas for the vector of means, and you have an updating formula for the covariance matrix. The nice thing here is that with that covariance matrix, you're taking advantage of the fact that if I observe a single x, that is the performance of a single drug or a single discretized price or testing out a single product, I get to update possibly the entire vector. Now, nonlinear models get tricky. Nonlinear models, we're trying to minimize the least squared errors, and this turns out to be a non-convex optimization problem. So if I have some starting point, and I happen to start at that one location, the search algorithm will trend toward a local optimum. If I start at a slightly different point, I might end up at a totally different local optimum. So you can do, what we do is we update these with gradient updates. Now, by the way, this is how we update neural networks. This is how we do any nonlinear estimation. Once we go to a model that's nonlinear, and again, I emphasize nonlinear in the parameters, these estimation problems become much more complicated. Often people are trying 20 different random starting points, optimizing from each starting point, and then just picking the best of the 20 optimized points. So this is not, whereas in recursive estimation for linear models, we get the exact answer with our single update. With nonlinear, all we're doing is saying, let's say I have an estimate, and then I get one more observation. Well, what you can do is blend in that one more observation and do one or maybe a small series of updates, but it's not recursive estimation. You're not getting the same answer you would get if you started from scratch. You're just adding one more data point and doing some more iterations, your gradient descent. By the way, I could do some more iterations, my gradient descent, even if I didn't have another data point. So this is why things get a little bit ugly. On my website, I don't actually at this time have a web page on estimation methods. My best reference for machine learning in the context of sequential decision problems is my chapter 3. Of course, machine learning is a massive topic with some fabulous books. My book is written to give you just a nice complete chapter, not as thorough as some of the major books on machine learning, but it covers all the major techniques, but it does so in the context of sequential decision problems.